Chase Ayers. This is my creative assignment 4 experiment, and I chose to do a Twizzler tensile test. So the outcome of this experiment is to observe and essentially quantify how a deformable body, being Twizzlers in this case, reacts to a pulling force, being tension. Some of the key concepts of deformable bodies in this experiment is first off with deformation. And in class, we define deformation as a change in the shape or size of an object due to applied force. We also went over elasticity, is when the object stretches but returns to its original shape when the force is removed. And then plasticity, being where the object stretches and is permanently changed even when the force is removed. So it's permanently stuck in the state that it is in. So for my procedure, the first step is getting Twizzlers and measuring the initial length, being L0 in this case, or around 20 millimeters. And then next I would add a paper clip to the bottom of the Twizzler, and I added and weighed certain fishing weights that I have and calculated those as F equals mg, being the weight of the weights. And then I would hang it from a chip clip and add the weights to the bottom, and then wait 10 seconds, and then measure the new stretched length L. As you can see, it's stretched around 21 millimeters, or 1 millimeter in this case, being the change in L, which is the deformation. And then I would repeat this process and continue adding more and more weight and measuring the change in L until the Twizzler eventually breaks. And then I recorded this data where I logged all the data pairs for analysis. And here is the data table. The initial length L0 was around 20 millimeters for all trials, but the point of failure was observed at around 2.5 newtons with a total deformation of 16 millimeters. So for each trial, I weighed and put on each weight with precision, where I went up in increments of 0.5 newton. So for trial 1, obviously, I went for 0.5 newton and it's changed 2 millimeters. For trial 2, I applied another half, making it 1 newton, and it changed 4 millimeters. And then for trial 3, again, I added a half, and it deformed 6 millimeters. And then in trial 4, with 2 newtons, it stretched to 9 millimeters. And then in trial 5, it eventually failed, where it deformed 16 total millimeters. So the key findings and analysis from this experiment is that the elastic region for the Twizzler is at low forces, being up to 1 newton, where the material is exhibited high elasticity. If the force was removed, the Twizzler did eventually almost completely return to the L0, which is 20 millimeters after measuring. So I kind of had to be quick with measuring the initial deformation. So for the plastic region and failure of the Twizzler, it was beyond 1.5 newtons, where the deformation became permanent or plastic, and the material reached its ultimate tensile strength and failed at approximately 2.5 newtons of applied weight or force. So how this relates to my major of mechanical engineering: it involves material science, where engineers performed this exact tensile test on real materials like steel, aluminum, and plastics. I kind of made it a little bit more simple with a piece of candy. This also applies to stress and strain curves, where the data from our experiment can be used to create a stress-strain curve, which is a fundamental graph in engineering, as well as the design for safety, which is important for knowing a material's elastic limit and failure point, which can allow engineers to design safe bridges, cars, and planes. and this can also help predict behavior, where this experiment is a tangible model for predicting how any structural material will behave under a load. So, in conclusion, the Twizzler is a ductile material as it experienced significant plastic deformation before failure. The Twizzler is not brittle, and it would have broken with very little deformation, and then you can apply this to the real world, in which the simple tensile test model can mimic the same principles used to test steel, concrete, and other building materials. So here are my references. Thank you.